Hot melt adhesives, chemistry, formulation, performance, and emerging developments. Hot melt adhesives, HMAs, are solvent-free, thermoplastic adhesive systems that are applied in the molten state and solidify upon cooling to form a bond. Unlike solvent-based or waterborne adhesives, HMAs contain 100% solid, eliminating the need for drying or curing processes. This feature provides advantages such as rapid processing, reduced environmental impact, and high efficiency. At room temperature, HMAs are solid materials. Upon heating, they soften or melt into a low to moderate viscosity liquid, enabling application onto substrates. Bond formation occurs through physical solidification, rather than chemical cross-linking, although reactive variants, e.g., polyurethane hot melts, may undergo secondary curing. Classification based on setting mechanism. The setting mechanism of HMAs is governed by polymer thermal transitions, particularly glass transition temperature, Tg, and melting temperature, Tm. Based on these, HMAs are classified into three categories. Class A, amorphous polymers, Tg, room temperature. Amorphous polymers with Tg above room temperature exhibit high stiffness and strength at ambient conditions, low elongation and brittle behavior. Due to their limited flexibility, these polymers are rarely used alone. Instead, they are modified through blending with low Tg polymers, use of block copolymers, e.g., styrenic systems. Such modifications improve toughness while retaining cohesive strength. Class B, semi-crystalline polymers, melting temperature, room temperature. Semi-crystalline polymers represent the most widely used class of HMAs. They are characterized by trademark above room temperature, Tg is significantly below room temperature. This combination yields good flexibility, low Tg, high strength and toughness, crystalline domains, reduced brittleness. Thermal behavior. Below Tm, mechanical strength is maintained. Above Tm, crystalline regions melt, causing rapid viscosity reduction. Examples: ethylene vinyl acetate, EVA, polyesters, polyamides. Limitations: formulation flexibility is restricted because additives may interfere with crystallization kinetics, affecting melting speed and mechanical integrity. Class C, high molecular weight polymers, Tg less than room temperature. These polymers exhibit very low Tg, well below room temperature, high molecular weight. They behave as viscoelastic, high viscosity fluids with some solid-like characteristics, e.g., shape retention. However, cohesive strength is low, load-bearing capacity is limited. Such systems are mainly used as sealants rather than structural adhesives. Formulation principles of hot melt adhesives. HMAs are complex blends where each component contributes to melt, processing, and durability. Base polymer, 30 to 100 weight%. Defines rheology and viscosity, mechanical properties, strength, flexibility, adhesion characteristics, and thermal stability and setting behavior. Tackifying resins, 30 to 100 weight%. Enhance, tack, initial stickiness, wetting of substrates, adhesion strength. Compatibility between resin and polymer is critical for transparency and performance. Plasticizers and waxes, 0 to 50 weight%. Provide reduced melt viscosity, lower application temperature, and improved flexibility. Waxes also control open time, working time, set time, solidification rate, largely influenced by crystallization behavior. Fillers, 0 to 50 weight%. Used to reduce cost, modify rheology, and improve thermal stability. However, fillers may disrupt crystallinity in semi-crystalline systems. Additives, less than 5 weight%, include antioxidants, thermal stability, rheology modifiers, adhesion promoters, and odor neutralizers. Chemistry of major hot melt adhesive systems. Polyolefin-based HMAs. Polyethylene, polypropylene, and their copolymers are low cost, chemically resistant, and easy to process. However, they exhibit poor adhesion to polar substrates and limited heat resistance. Applications include packaging and bookbinding. Ethylene vinyl acetate, EVA, hot melts. EVA-based HMAs account for approximately 70% of the market due to their excellent price-performance balance. Synthesis. Produced via free radical copolymerization of ethylene and vinyl acetate, sometimes modified with acidic functionalities. Key properties. Good adhesion to diverse substrates, low viscosity and moderate processing temperatures, and low toxicity. Important parameters. Vinyl acetate content, less than 20%, low, approximately 30%, medium, 30%, high, greater flexibility and adhesion, higher cost. Softening point, 80 to 150 degrees Celsius, determined via ring and ball method. EVA HMAs are widely used in packaging, woodworking, and DIY applications. Polyester hot melts. Polyester HMAs are high-performance systems offering superior adhesion, especially to plasticized substrates, high heat resistance. However, they are more expensive and complex to manufacture, approximately 5% market share. Polyamide hot melts. Polyamides provide strong adhesion to various substrates, high heat resistance. Good chemical and hydrolytic stability. They are more flexible than polyesters and exhibit lower processing viscosities, approximately 10% market share. Property control. Copolymerization reduces crystallinity and the melting point. Incorporation of secondary diamines, e.g., piperazine, reduces hydrogen bonding. Long-chain diamines and polyethers improve flexibility. Fundamental understanding of adhesive behavior. Mechanical and viscoelastic behavior. The adhesive performance of HMAs depends on thermal transitions, Tg, Tm, viscoelastic properties, and interfacial adhesion. Experimental studies using DSC and DMTA show strong correlations between thermal properties, viscoelastic response, and shear strength. Adhesive strength decreases with increasing temperature, with brittle failure at low temperature, plastic failure at high temperature. Role of polymers. Polymers govern melt viscosity and rheology, cohesive strength, flexibility, adhesion. For example, increasing vinyl acetate content in EVA improves adhesion and flexibility but increases cost. Recent developments include hollow polymer microspheres, reduced density, improved green strength, ionomer-based HMAs, thermoreversible cross-linking systems, ionic, physical crosslinks. Role of other ingredients. Tackifiers. Lower Tg tackifiers increase tack, reduce crystallinity and enhance adhesion. Waxers. Control open, set times, influence crystallization kinetics. Plasticizers. Affect miscibility and mechanical properties. Additives. Improve odor, stability, and processing. Interactions between ingredients are complex and can significantly affect performance. Blending behavior and microstructure. HMAs are multi-component systems, and their performance depends on miscibility, phase morphology, and interfacial interactions. Studies show partial miscibility in polymer blends, morphology strongly influences adhesion. However, predicting behavior in complex blends remains challenging due to competing interactions. Technological challenges and improvements. Limitations. Limited heat resistance, high application temperatures, greater than 150 degrees Celsius, safety concerns during processing, poor performance under sustained load. Advances. Development of warm melt adhesives, lower application temperature, improved processing systems, controlled heating, new polymer formulations for better thermal performance. Development of new types of HMAs. Reactive HMAs. Moisture-curable polyurethane systems provide improved heat resistance and durability. Radiation-curable HMAs. Cross-link upon UV exposure, enhanced high-temperature performance. Biodegradable HMAs. Based on polylactide, PLA, polycaprolactone, PCl, limited by cost and thermal stability. Environmental considerations and green HMAs. Challenges. Dependence on petroleum-based raw materials, limited biodegradability, and recycling incompatibility. Green strategies. Use of renewable polymers, PLA, PHB, natural tackifiers, rosin, terpenes, and biodegradable waxes. Limitations. Poor thermal stability, compatibility issues, and trade-offs between water resistance and recyclability. Future perspectives. Future research should focus on structure-property relationships, crystallization thermodynamics and kinetics, multi-scale modeling and simulation, development of fully compatible, biodegradable systems. A deeper understanding of microstructure and intermolecular interactions is essential for designing next-generation HMAs. Conclusion. Hot melt adhesives are versatile, solvent-free materials widely used across industries due to their rapid processing and ease of application. Their performance is governed by polymer chemistry, thermal transitions, and complex interactions among formulation components. While conventional systems such as EVA dominate the market, Ongoing research is focused on improving heat resistance, lowering processing temperatures, and developing environmentally sustainable alternatives. Achieving these goals requires a shift from empirical formulation toward a fundamental understanding of structure-property relationships, enabling rational design of advanced HMA systems.